Alright, we're back talking more about iterated integrals, and our goals for today are to take slightly more complicated regions and set up iterated integrals for those regions. And then we want to continue to use iterated integrals to find net volume under graphs and to even find the volume between two different graphs. Sort of like we found the area between two functions back when we were working in Calculus 2. So let's go ahead and get started with the following exercise. So someone comes to us and they say, let R be the triangle in the xy plane with the vertices at 2, -1, -2, -1, and -1, -1. So part 1, set up an iterated integral of a generic function f of xy over the region R using the order dx dy. So, as always, this translation from a general double integral to an iterated integral begins by drawing the region R in the xy plane. So, let's sketch in the vertices 0, 0, the vertices at 2, -1, and the vertex at -2, -1. So here we are, 2, -1, -2, -1, and here is our region. Alright, now recall that when we are trying to set up an iterated integral in the order dx dy, our first objective are to find the functions which bound our region on the right-hand side and on the left-hand side, right and left being the directions corresponding to x. So here is the function bounding our region on the right side, this slanted line. Now, my first inclination, anytime I go to find the equation of a line, is to find it with y as a function of x, just because that's how we're taught to interpret the slope of a line. So this function goes over 2, down 1, and this would be y equals -1/2 x. But we need this y as x as a function of y, so I'll think of this as x is equal to -2y. So this is the function that bounds our region on the right side. And on the left side, we have the line going from -2, -1 to the point 0, 0. And so this would be the line with slope +1/2, aka x equals 2y, is what bounds this region on the left. Now, if I look amongst this region for the full set of y coordinates, the highest y coordinate, the largest y, is going to be y equals 0, corresponding to the top of the triangle. And the lowest y is going to be y equals -1, corresponding to the bottom of the triangle. So based on that, let's set up our iterated integral. The y values go from -1 to 0 on the outside, and the x values go from on the left 2y, on the right -2y. And that would be the limits of integration for this generic function using the order of integration dx dy. That would be my final answer to this problem that asks me to set up an integral. Not to calculate it, not just yet, just to set it up. Part 2, same region, same unknown function, but this time they want the order dy dx. So as before, let's go ahead and let's draw the region. This triangle, and let's try and ask ourselves what function would bound this region on the top, and what function would bound this region on the bottom. The problem is that at about the halfway mark through the region, the top function changes from y equals 1/2 x to a different top function of y equals negative 1/2 x. So we have two top functions. One valid on the left side of the region, where the x values go from -2 to 0. The other one valid on the interval of x's, x going to the right half of the region from 0 to 2. Now, just as in Calculus 1, anytime you encountered a region with a sudden shift in behavior like this, where there was a corner in the region, that meant that you had to set up two integrals in order to calculate that. You essentially have to subdivide the region and cut it in half and set up an integral over one region and a separate integral over another region to deal with the fact that you have two different top functions on these two subregions. So let's subdivide this and let's set up an integral over region 1 and combine that with an integral over region 2. Over region 1, let's make that pink. And let's do a separate integral for the region called 2, which has a different top function. All right, now for region number 1, which has a top function of y equals positive 1/2 x, the bottom function is y equals -1, that flat constant value here, this constant function. And the same thing is true on the other half of the region, y equals -1. So the pink region, for its inner limits of integration, is going to go from the lowest y value, y equals -1, to the topmost y value, y equals 1/2 x on that region. Then we have to consider the lowest and the highest x-coordinate amongst all the points in region number 1, which stretches from x equals -2 up to x equals 0. So the lowest x-coordinate for region 1 is -2, and the highest x-coordinate is 0. Now for the second half of the triangle, the one after the corner, we have a lower y limit of y equals -1 and an upper y limit of y equals -1/2. And this region is valid for the x-coordinates going between 0 and +2. X goes from 0 to +2. And this would be with the limits of integration in the order dy dx as specified. So in order to integrate the region with the limits dy dx, we actually need two separate iterated integrals because the top function for the region changes as soon as we hit this cusp here, the corner, this vertex of the triangle. Now this example is meant to demonstrate that from time to time, one order of integration will be demonstrably clearly superior to the other. Even though I think that for many students, integrating with respect to x first is not very natural, in this instance, integrating with respect to x has the clear advantage because it only required you to set up a single iterated integral to capture the behavior of the entire region. Alright, now someone says to me in part 3, using whatever order of integration you prefer, whether you like dx dy or dy dx, calculate the net volume under the graph of this function, f of xy equals x squared minus y over the region R. Now, obviously, I think based on what I've been saying, it's pretty clear which one I prefer, which is with x coming first. The integral from -1 to 0, from 2y to -2y, where x came first and then y. And here is our specific function, x squared minus y. So let's go ahead and calculate that, working from the inside out as usual. Now first, I'm going to integrate with respect to x, treating y as a constant. And so I'm just going to leave the outermost limits of integration alone. And I'm going to pretend that y is constant, and I'm going to find the antiderivative of x squared minus y. Now let's do this one term at a time. The antiderivative of x squared with respect to x is x cubed over 3 by the power rule. Now what is the antiderivative of y? Be careful because it's not y squared over y over 2. Y is essentially like 5 here. It's a number. And the integral of a number is that number times your variable. So the antiderivative of y with respect to x is y times x. And let's evaluate that from x equals 2y to x equals minus 2y. Okay. Now, still leaving our outermost limits alone. Here is our inner limit. So let's plug in -2y. That cubed would be -8y cubed over 3. X equals -2y. And then let's subtract what we get when we plug in +2y. And then +2y. And then simplify. Now if you're saying to yourself, Sam, these integrals are already too long, just you wait. Just you wait, because this is just a double integral, and triple integrals are coming any minute now. Any minute now, we are going to have triple integrals, which will be even longer than these. All right. Having simplified the integrand, let us iterate and integrate with respect to y. So let's use power rule to find the antiderivative, and we have -4 over 3, y to the 4th power, and we have +4 over 3, y to the 3rd power, which will evaluate from -1 to 0. And if we plug in those limits and subtract, plugging in 0 will cause the entire quantity to vanish, and plugging in -1 will give us -4/3 minus 1 to the 4th power plus 4/3 minus 1 to the 3rd power. And so some arithmetic will get this done. This looks like 4/3 plus 4/3. This looks like a net volume of 8/3. And so here is the power of the iterated integral. It gave us the ability to calculate the net volume under this function over the region R. In this case, we had to essentially choose the order of integration that we wanted to use when we set up our iterated integral. But one, I think, was a superior choice over the other in terms of simplicity. Okay, now let's do one more example of this idea, where we find not the volume underneath a certain surface underneath the graph of a 2D function, let us find the volume between two surfaces. And the idea is very similar to what we had in Calc 2. Suppose that f of xy is greater than or equal to g of xy. So one function is on top of the other on the region R. To find the volume that is trapped between the graphs of f of xy and g of xy over the region R, all you have to do is integrate top minus bottom function. Same as it was back in Calculus 2. Integrate top function minus bottom function. Now let's try it with this example. Find the volume between the plane z equals x plus y plus 10 and the graph of z equals x squared plus y squared over the region -1, 0 to 0, 2. Now, when the question is given to you in this format, it is your job to determine which function is on top of the other, which function is on the top of the region, and which function is on the bottom. Well, folks, I have to admit, it took me a long time to find a graphing calculator online that actually was, that I actually found easy to manipulate the axes. And this is the best one that I've found so far. I have no idea where I am. I suppose this is CalcPlot 3D at some .edu website. Who knows? But I Googled and tried different things until I found a calculator that did what I wanted. So here we can see the graph of x squared plus y squared drawn over the region R, and that's this little slice here. And we can see it's very, very far below the plane, which is x plus y plus 10. So technologically, we can use the graph to deduce which function is on top of another function in this region. Now, considering the rigmarole that I just went through to get a technological graph that I could actually make sense of, it may be easier to do a slightly more manual technique to tell which function is on top in this region, and that is just to test a few points. For example, at x equals 0, 0, which is in this region, corresponding to the right corner of the x interval and the left end of the y interval. If we plug this in, 0 plus 0 plus 10 is the output of the plane. 0 plus 0 is the output of the paraboloid, z equals x squared plus y squared. And so I would, based on that, getting a larger value from the plane, we also see that this function is going to be the one on top in this region, and this will be the one on the bottom. All right, so based on that, let's integrate the difference between the top function and the bottom function over this region. Now knowing that the plane is above and has larger values than the paraboloid. Now, rectangular regions like this R, which goes from -1 in the x direction to 0, and 0 up to 2. Rectangular regions like this are extremely convenient because the top function is just the constant y equals 2. The bottom function is just the constant y equals 0. The leftmost x is -1, the rightmost x is 0, and so all the limits of integration here are just numbers. Integrate from 0 to -1, integrate from 0 to 2. The function that we're integrating is top function, x plus y plus 10, minus bottom function, x squared plus y squared. And we're integrating this where y comes first and x comes last. Although you could just as easily integrate this with y coming last and x first. Okay, now let's simplify the integrand just a little bit. integral from 0 to minus 1, integral from 0 to 2, and let's just clean this up. We have negative x squared, negative y squared, plus x, plus y, plus 10. First with respect to y, and then with respect to x. Alright, working from the inside out, we have the integral from 0 to minus 1, and then let's take the antiderivative with respect to y. Treating x as a constant, we have negative x squared times y, then power rule, negative y cubed over 3, x is a constant, so plus x times y, power rule, y squared over 2, and then 10 is a constant, 10y dx. And let's evaluate that from the limits y going from 0 to 2. So based on that, we now have the integral from 0 to minus 1. Then replacing y with 2, we get negative 2x squared. Replacing y with 2, we get negative 8 thirds. Then plus 2x, and then plus 4 over 2, and then plus 20. Plugging in 0 will cause each of these terms to vanish. Okay, let's do just a little bit of cleaning up. Negative 2x squared plus 2x, and then let's combine these constants. So 4 over 2 will be 2, take away 8 thirds will be negative 2 thirds, and plus 60 thirds will be 58 thirds, if that arithmetic is correct. Alright, finally integrating one more time with respect to x, we have negative 2 thirds x cubed, x squared, 58 thirds times x, plug in 0 and minus 1, which I have unfortunately in the wrong order, excuse me. Minus 1 should of course be on the bottom, since it's the lowest value. I apologize. Let's just swap these around. Alright, plugging in 0 will cause each of these terms to vanish, and then plugging in negative 1 will give us this number, which I will leave to you to simplify if you desire. So a fairly lengthy process,